Linear Algebra II, Lecture 8, Problem Session. Problem 1. Show that there is a unique linear map F from R3 to R2, which maps the vector 1, 1, 1 to the vector 1, 1, which maps the vector 1, 1, minus 1 to the vector 0, 1, and which maps the vector 1, minus 1, 1 to the vector 1, 0. Determine the matrix of this linear map in the standard basis. Determine a basis in the kernel of F and a basis in the image of F. And determine whether the linear map F is invertible or not. Solution. Let us denote by V1 the vector 1, 1, 1, by V2 the vector 1, 1 and minus 1, and by V3 the vector 1, minus 1, 1. So our map F is defined by its values on these three vectors. In other words, we know the values f of V1, f of V2, and f of V3. Since we also know that f is linear, then for any linear combination of these three vectors, so for any vector of the form lambda 1 V1 plus lambda 2 V2 plus lambda 3 V3, from the linearity of f, we deduce that the value of f at this linear combination is equal to lambda 1 times f of V1 plus lambda 2 times f of V2 plus lambda 3 times f of V3. So, knowing the values of f at V1, V2, and V3, we can find out what is the value of f on any linear combination of these three vectors. So it's natural to ask the question, can we express any vector w in R3 as a linear combination of the vectors V1, V2, and V3? So in other words, do V1, V2, and V3 generate R3? But since we have three vectors in a three-dimensional vector space, equivalently, we can ask whether the vectors V1, V2, and V3 form a basis of R3. And to find this out, we should write these vectors as columns in the matrix and compute its determinant. So the determinant of the matrix, which when we read column-wise 1, 1, 1, 1, 1, minus 1, and 1, minus 1, 1. These are exactly our vectors V1, V2, and V3. So now the determinant of this matrix is equal to 1 times 1 times 1 plus 1 times 1 times minus 1 plus 1 times 1 times minus 1 minus 1 times 1 times 1 minus 1 times minus 1 times minus 1 and minus 1 times 1 times 1. And this is equal to minus 4, which is not equal to 0. And it follows that V is indeed a basis of R3, and therefore F is uniquely defined, because then it means that every element in R3 can be uniquely written as a linear combination of V1, V2, and V3. And from the above, we have a unique value of F at such a linear combination. So this proves part A of our problem. Directly from the formulation, we have that the matrix of F, if we fix the basis V in R3 and the standard basis E in R2, then the matrix of F in these bases will be the matrix which we read column-wise 1, 1, 0, 1, 1, 0. So this is because by the formulation 1, 1 is the image of V1, 0, 1 is the image of V2, and 1, 0 is the image of V3. So we know the matrix of F in these bases, but we need to determine it in the standard basis. In order to do that, we need the base change formula. We are not going to change the basis in R2, we already have the standard basis there, but we want to have also the standard basis in R3. So the relevant base change formula is that the matrix of F in the standard basis is equal to the product of the matrix of F in the basis V and E times the transformation matrix from V to E. So this V as a lower index and this V as an upper index, they should cancel. By definition, we know the transformation matrix from the standard basis to V. This is exactly the matrix which we get when we write our vectors V1, V2, and V3 as columns. So we know the transformation matrix from E to V, but we need the transformation matrix back from V to E. And we know that the transformation matrix back is just the inverse. So we need to find the inverse of this matrix. Let's do this computation. So we write our matrix as the left-hand side, then the vertical line, and then the identity matrix. So now we need to reduce the left-hand side to the identity matrix using Gauss elimination. So we have 1 in position 1, 1. So we use it to eliminate everything else in the first column. So we subtract row 1 from row 2 and from row 3. Row 1 remains the same, and row 2 becomes 1 minus 1 is 0. 1 minus 1 is 0. Minus 1 minus 1 is minus 2. 0 minus 1 is minus 1. 1 minus 0 is 1. 0 minus 0 is 0. And row 3 becomes 1 minus 1 is 0. Minus 1 minus 1 is minus 2. 1 minus 1 is 0. 0 minus 1 is minus 1. 0 minus 0 is 0. 1 minus 0 is 1. So now it is convenient to change the rows 2 and 3. So row 1 remains the same, row 3 becomes row 2, and row 2 becomes row 3. And now we multiply both row 2 and row 3 with minus 1/2 to get 1s on the diagonal. So row 1 remains the same, row 2 becomes 0, 1, 0, 1/2, 0, minus 1/2, and row 3 becomes 0, 0, 1, 1/2, minus 1/2, 0. And now we have to kill these ones. So we have to kill 1 here. For this, we should subtract row 2 from row 1. And to kill this one, we subtract row 3 from row 1. So we subtract both rows 2 and rows 3 from row 1. Rows 2 and 3 remain the same, and row 1 becomes 1 minus 0 minus 0 is 1. 1 minus 1 and minus 0 is 0. It should be 0 here. 1 minus 0 minus 1 is 0. It should be 0 here. 1 minus 1/2 minus 1/2 is 0. 0 minus 0 minus minus 1/2 is 1/2. 0 minus minus 1/2 minus 0 is 1/2. Consequently, the transformation matrix from V to E is the matrix 0, 1/2, 1/2, 1/2, 0, minus 1/2, 1/2, minus 1/2, 0. So note that there are typos here. These two elements should be 0. So now we can do the computation. The matrix of F in the standard basis is equal to the product of the matrix of F in the basis E and V times the transformation matrix from V to E. So the matrix of F is 1, 0, 1, 1, 1, 0 times the transformation matrix, which is 0, 1/2, 1/2, 1/2, 0, minus 1/2, 1/2, minus 1/2, 0. So when we compute this, we will get 1/2, 0, 1/2, and then 1/2, 1/2, 0. So the matrix of F in the standard basis is a matrix 1/2 times 1, 0, 1, 1, 1, 0. And this solves part B of our problem. To determine a basis in the kernel of F, we need to solve the homogeneous system of linear equations whose matrix is exactly the matrix of F in the standard basis. Of course, we can ignore the 1/2 multiple, so we need to solve the homogeneous system of linear equations whose matrix is the matrix 1, 0, 1, 1, 1, 0. And here we can note that this matrix is in a sort of row echelon form if we interpret row echelon form quite in a free way. So we have here something which is up to permutation of columns and identity matrix. So our leading elements are this element in row 1 and this element in row 2. So we can take x1 as a free variable, And for the free variable, we have the trivial equation x1 is equal to x1. From the second row, we have that x2 is equal to minus x1. And from the first row, we have that x3 is equal to minus x1. In the vector form, we have thus the equation x1, x2, x3 is equal to x1 times 1 minus 1 minus 1. So this means that the vector 1 minus 1 minus 1 forms a basis in the kernel of f, because it's a basis in the set of all solutions to our homogeneous system of linear equations. And of course, since the kernel of f is non-zero, the map f is not invertible. So this answers the last part, D. So we are almost done, but we still need a basis in the image of f. For this, we look at our matrix of f in the standard basis and our leading elements, which are for the first row in column 3 and for the second row in column 2. So therefore, this means that the corresponding columns form a basis in the image of our linear map f. So this should be f. And again, we can ignore the 1/2 scalar, so the corresponding vectors 0, 1 and 1, 0 form a basis in the image of f. And one can note that this is exactly the standard basis in R2, but inverse order. And this completes part C of our problem and hence the whole problem. Problem 2. Let G be a linear map from the space of all polynomials of degree at most 3 to the space of all polynomials of degree at most 2, which has the following matrix in the standard basis. So the matrix of G in the standard basis is a matrix 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0. A. Show that there is a polynomial f of x in Rx3 such that the image of f of x under G is equal to 2 plus 2x plus x squared. B. Shows that there is no polynomial h of x in Rx3 such that the image of h of x under G is equal to 1. Solution. Let us use the coordinates with respect to the standard basis. Then the question in A can be formulated as follows. If we look at the coordinates of the image of G under F in the standard basis, then by the main properties of coordinates and the matrix of the linear map, so this is equal to the product of the matrix of the linear map times the coordinates of F in the standard basis, and this should give us the coordinates of the vector 2 plus 2x plus x squared in the standard basis. And these coordinates are 2, 2, 1 by definition. In other words, to show that such f of x exists, we need to show that the non-homogeneous system of linear equations, whose matrix is the matrix of G in the standard basis, and whose right-hand side is the vector 2, 2, 1, we need to show that such system has a solution. And similarly, for the part B, we have the system of linear equations where we have the matrix is the matrix of G in the standard basis, then we have the coordinates of H in the standard basis, and this product should be equal to 1, 0, 0. So to solve B, we need to show that such non-homogeneous system of linear equations does not have any solutions. So let's try to solve both systems at the same time by writing the matrix of the system, then vertical line, then the right-hand side for the first system, again a vertical line, and the right-hand side for the second system. And solving systems of linear equations means reducing such a matrix to a row echelon form using Gauss elimination. So we have 1 in position 1, 1. We can use it to kill all other elements in its column. So we subtract row 1 from row 2 and row 1 from row 3. Row 1 remains the same. Row 2 becomes 1 minus 1 is 0. 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 2 minus 2 is 0. 0 minus 1 is minus 1. And row 3 becomes 1 minus 1 is 0, 0 minus 1 is minus 1, 1 minus 1 is 0, 0 minus 1 is minus 1, 1 minus 2 is minus 1, 0 minus 1 is minus 1. So now we can change rows 2 and 3 and multiply this third row by minus 1. Row 1 remains the same. Row 2 becomes 0, 1, 0, 1, 1, 1, and row 3 becomes 0, 0, 0, 0, 0, minus 1. And finally, we use this 1 in position to 2 to kill everything else in its column, so we subtract row 2 from row 1. Rows 2 and 3 remains the same, and row 1 becomes 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0, 2 minus 1 is 1, 1 minus 1 is 0. So this is the matrix which we obtained. This is now our row echelon form. And if we look at the first system of linear equations, so this corresponds to the first 5 columns in this matrix, then we see that the rank of the matrix which is formed by the first 2 columns is 2, because we have 2 non-zero rows. And this is equal to the rank of the matrix formed by the first 5 columns. So if we add the right-hand side, we have the same rank, also 2 non-zero columns. This means that the first system of linear equations has a solution. At the same time, if we delete column number 5, which means if we look at the second system of linear equations, then still for the first 4 columns we have 2 non-zero columns, so the rank is 2. But when we add the last column, column 6, we have that the third row is also non-zero. So the rank of the extended matrix of that system is 3. Therefore, the rank of the matrix is 2 and of the extended matrix is 3. This means that that system does not have a solution. And this completes problem 2. Problem 3. Let R from R3 to R3 be the linear map which geometrically is given as a reflection with respect to the plane x plus y plus z is equal to 0. Determine the matrix of R in the standard basis. Solution. An alternative way to describe a reflection with respect to the plane is by the following properties of this map. First of all, it stabilizes every element on the plane. If we have a vector in the plane and reflect this vector with respect to the plane, we get the vector back. And the second property, it sends the normal vector n, the normal to the plane, to its negation minus n. And intuitively one can think of a reflection as if our plane is a giant mirror and the linear operator R is the operator of taking the mirror image of the vector with respect to this mirror. So how we can solve this problem? We can determine the matrix of this linear map if we choose a basis wisely. So if we take as basis elements in the plane or the normal vectors. And then we can use the base change formula to determine the matrix of R in the standard basis. So let's do the work. So a plane in R3 has dimension 2. So let us choose 2 linearly independent vectors in our plane x plus y plus z is equal to 0. For example, we can take as v1 the vector 1 minus 1, 0, because 1 plus minus 1 plus 0 is 0, so it belongs to the plane. And we take as v2 the vector 0, 1, minus 1, because 0 plus 1 plus minus 1 is equal to 0, so this vector is also in the plane. These vectors are obviously linearly independent because they are not scalar multiples of each other. And as the third vector, we take the normal to the plane. This is a vector 1, 1, 1, the vector of coefficients in our linear equation. So let us now check that v1, v2, and v3 forms a basis in R3. So we write the coordinates of these vectors into a matrix and compute the determinant. So the determinant of the matrix 1, 0, 1, minus 1, 1, 1, 0, minus 1, 1 equals 1 times 1 times 1 plus 1 times 0 times 0 plus 1 times minus 1 minus 1 times 1 times 0 minus 1 times minus 1 times 0 and minus 1 times 1 times minus 1. So if we compute all this, we will get 1 plus 0 plus 1 minus 0 minus 0 plus 1. And this is equal to 3, which is not 0. So these vectors indeed form a basis in R3. With respect to the basis V, we have the following. Since the vectors v1 and v2 belong to our plane, then the value of r at v1 is equal to v1 and r of v2 is equal to v2. And also, since v3 is normal to the plane, we have that r of v3 is equal to minus v3. Therefore, the matrix of R with respect to our basis V is the diagonal matrix with 1, 1, and minus 1 on the diagonal. So this one means that R of V1 is V1, this means that R of V2 is V2, and this means that R of V3 is minus V3. And we also know, more or less by definition, that the transformation matrix from the standard basis to V is the matrix column-wise 1, minus 1, 0, because this is V1, 0, 1, minus 1, this is V2, and 1, 1, 1, this is V3. And to use the base change formula, we would also need to know the transformation matrix from V to E, which is the inverse of the transformation matrix from E to V. So we need to find the inverse of this matrix. So here is the computation. We write our matrix as the left-hand side, then the vertical line, and then the identity matrix on the right. And we use Gauss elimination to reduce this matrix to the form when we have the identity matrix on the left-hand side. So we have here 1. We can use it to kill this minus 1. So we add row 1 to row 2. Rows 1 and 3 remain the same, and row 2 becomes minus 1 plus 1 is 0. 1 plus 0 is 1, 1 plus 1 is 2. 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0. So now we can use this one to kill this minus 1. So when we add row 2 to row 3, we will get that rows 1 and 2 remain the same, and row 3 becomes 0 plus 0 is 0, 1 plus minus 1 is 0, 2 plus 1 is 3, 1 plus 0 is 1, 1 plus 0 is 1, and 0 plus 1 is 1. So now we need to make 1 here, so we divide row 3 by 3. Rows 1 and 2 remain the same, and row 3 becomes 0, 0, 1, 1 third, 1 third, 1 third. And now we have 1 here, and we can eliminate this 2 and this 1. So we subtract row 3 from row 1, and we subtract twice row 3 from row 2. Row 3 remains the same. Row 1 becomes 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 1 third is 2 thirds, 0 minus 1 third is minus 1 third, 0 minus 1 third is minus 1 third. And row 2 becomes 0 minus 0 is 0, 1 minus 0 is 1, 2 minus 2 times 1 is 0, 1 minus 2 times 1 third is 1 third, 1 minus 2 times 1 third is 1 third, 0 minus 2 times 1 third is minus 2 thirds. Consequently, the transformation matrix from V to the standard basis is 1 third of the matrix 2 minus 1 minus 1, 1, 1 minus 2, 1, 1, 1. So now we can use the base change formula and compute that the matrix of R in the standard basis is the product of the transformation matrix from E to V, then the matrix of R in V, and then the transformation matrix from V to E. So we can move out the global scalar 1 third. Then we have this is the transformation matrix from E to V. This is the matrix of R in the basis V. And this is what remains from the transformation matrix from V to E. So 1/3 is the global scalar in the front. So this is equal to 1/3 times, so let's take the product of these two matrices. So here it means we add row 1 and row 3. We'll get 1, 0, -1 here. So this means the sum of this minus this. -1, 1, -1. And the last is row 3 minus row 2. 0, -1, -1. This is this matrix. Now we multiply it with the matrix 2, -1, -1, and so on. We'll get 1 divided by 3 times. So here, row 1 minus row 3. 1, -2, -2. Now here, minus this, plus this, minus this. -2, 1, -2. And finally, minus this, minus this. -2, -2, 1. Answer: the matrix of R in the standard basis is the matrix 1/3 of the matrix 1, -2, -2, -2, 1, -2, -2, -2, 1. Problem 4. Let S from Rx2 to Rx2 be the map which is defined as follows. S sends the polynomial f of x to the polynomial f of x plus 1. Prove that S is linear. Determine the matrix of S in the standard basis. Determine the matrix of S in the basis x, 1 plus x, and -1 plus x squared. So this basis is denoted by bold F. Shows that S is invertible. And find some element f of x in Rx2 such that the image of this f of x under S is equal to 1 plus x squared. Solution. Let us start by checking the linearity. For any two polynomials f and g in Rx2, if we apply s to f of x plus g of x, then, by the definition of the sum of two polynomials, this is applying s to the polynomial f plus g evaluated at x. So if we apply s to any polynomial, we should take that polynomial and evaluate it at x plus 1. So we'll get f plus g evaluated at x plus 1. But then by the definition of the sum of two polynomials, this is equal to f of x plus 1 plus g of x plus 1. And by the definition of s, f of x plus 1 is exactly the value of s at f of x, and g of x plus 1 is exactly the value of s at g of x. So similarly for multiplication with scalars, for any polynomial f and the scalar lambda, s applied to lambda times f of x is the same as s applied to lambda f evaluated at x. By definition, this is lambda f evaluated at x plus 1. By definition of scalar multiplication of polynomials, this is lambda times f of x plus 1, and then f of x plus 1 is s of f of x. And this completes part A, so we have shown that S is a linear map. So the standard basis in Rx2 consists of the polynomials 1, x, and x squared. So to determine the matrix of S in the standard basis, we just compute the values of S at these polynomials. So S of 1 is equal to 1. There is no x, so there is nothing to shift here. S of x is x plus 1. And S of x squared is x plus 1 squared, which is 1 plus 2x plus x squared. So now we write the coefficients of these results as columns in the matrix, and what we get is the matrix of S in the standard basis. So the first column is 1, 0, 0, so this is a coefficient of 1. The second column is 1, 1, 0, and the last column is 1, 2, 1. So this is a matrix of S in the standard basis, and this completes part B. By definition, the transformation matrix from the standard basis to F is the matrix column-wise 0, 1, 0, 1, 1, 0, -1, 0, 1. So this is because F consists of x, 1 plus x, and -1 plus x squared. So let us check, just to be sure, that F is a basis. The determinant of this matrix is equal to 0 times 1 times 1 plus 1 times 0 times 0, plus 1 times 0 times minus 1, all this is 0 so far, minus 1 times 1 times 0, minus 0 times 0 times 0, minus 1 times 1 times 1. So this is minus 1, which is non-zero, so this is indeed a basis. And to apply the base change formula, we need the inverse of the transformation matrix from the standard basis to F. So let's compute this. So we write our transformation matrix from the standard basis to F, then the vertical line, then the identity matrix, and we do the usual reduction to the row echelon form using Gauss elimination. So here we have 1 in position 2, so we swap rows 1 and 2. So row 2 becomes row 1 becomes row 2, and row 3 remains the same. So now in this matrix, it's easier first to eliminate this minus 1 using this diagonal 1. So we add row 3 to row 2. Rows 1 and 3 remain the same, and row 2 becomes 0 plus 0 is 0, 1 plus 0 is 1, minus 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 0 is 0, and 0 plus 1 is 1. And finally, we kill this 1 by subtracting row 2 from row 1. So rows 3 and 2 remain the same, and row 1 becomes 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 0 is 0, 0 minus 1 is minus 1, 1 minus 0 is 1, 0 minus 1 is minus 1. So consequently, the transformation matrix from F to SD is the matrix minus 1, 1, minus 1, 1, 0, 1, 0, 0, 1. So this is exactly the right-hand side here. So now we can use a base change formula. So the matrix of S in the basis FF is equal to the product of the transformation matrix from F to the standard basis times the matrix of S in the standard basis times the transformation matrix from the standard basis to F. So this STD and this STD should cancel, and this STD and this STD should cancel. So this is a product of these three matrices. So this is a transformation matrix from F to STD right here. This we saw was the matrix of S in the standard basis, and this is the transformation matrix from the standard basis to F. So if we multiply these two matrices, we will get, so it's a middle minus the first and minus the third. So minus 1, 0, 0. Then the sum of the first and the third, 1, 1, 2. And then just the third row, 0, 0, 1. And now if you multiply these two matrices, so the first row should be just minus. So 0 minus 1, 1. Then first, second, and 2 times third, 1, 2, 1. And finally just the third row, 0, 0, 1. So this means that the matrix of S in the basis F is the matrix 0, minus 1, 1, 1, 2, 1, 0, 0, 1. And this answers C. In order to show that the linear map S is invertible, we just need to show that the determinant of the matrix of S in any basis, for example, in the standard basis, is non-zero. The matrix of S in the standard basis is the matrix 1, 1, 1, 0, 1, 2, 0, 0, 1. This is an upper triangular matrix with ones on the diagonal, so its determinant is 1, and this is not 0. And so S is invertible. Alternatively, one can argue that the inverse of S maps the polynomial f of x to the polynomial f of x minus 1. So S changes x to x plus 1. If we change x to x minus 1, we will get our original polynomial back. Consequently, if we want to know which polynomial is mapped by S to 1 plus x squared, we should just start from 1 plus x squared and replace x by x minus 1. So we will get 1 plus x minus 1 plus x minus 1 squared, and this is exactly the polynomial 1 minus x plus x squared. And we can check. If you take 1 minus x plus x squared and apply S, you will get 1 minus x plus 1 and then plus x plus 1 squared, which is exactly 1 plus x squared. And this completes part E and the whole problem. Some additional questions and problems. Question 1. Show that the map H from Rx2 to Rx2, which sends f of x to f of x minus f of x minus 1, is linear. Question 2. Find some bases in the kernel and some bases in the image of the linear map H from the previous question and determine whether H is invertible. Question 3. Let A be the matrix 1, 2, 1, 1. So this is a 2 times 2 matrix. The map F from the set of all 2 times 2 real matrices to itself maps a matrix X to AX A inverse. Prove that F is a linear map and determine the matrix of F in the standard basis. Question 4. The map G from Rx2 to Rx2 is given as follows. G applied to the polynomial f of x is equal to the derivative of x times f of x plus 1. Prove that G is a linear map and determine the matrix of G in the standard basis. Question 5. Determine the matrix in the standard basis for the linear map R from R3 to R3, which is a reflection with respect to the plane x plus y minus z is equal to 0. Thank you very much and see you next time.